So I would like to thank Lockheed Martin for their continued support and sponsorship of the robotics seminar series. Our speaker today is Professor Tomas Lozano-Perez, who is currently the School of Engineering Professor in Teaching Excellence at MIT. He's part of the CSAIL MIT. His research is at the intersection of robotics, computer vision, machine learning, medical imaging, and computational chemistry. But more recently, he's been looking at integrated task, motion planning, and then decision theoretic planning. He's won a number of awards, but I'll only talk about one. He's a recipient of the 2011 IEEE Robotics Pioneer Award, which, as you can imagine from the name, is one of the top awards that's given by the IEEE Robotics Society. And he won this for his pioneering work in configuration space motion planning, robotics and automation algorithms, and computational structural biology. So it's a great pleasure to introduce Tomas, and I look forward to an excellent talk. So Tomas, whenever you're ready, we can get started.
Thank you very much, and thank you for inviting me in this very weird time, but I'll hope to not bore you. So I'm going to be talking about learning and using composable robot skill. This is joint work with Leslie Kevlin. She and I have run a group for about 15 years and at the intersection of robotics and machine learning. So I'll try to talk about that. Now, by way of context, let me kind of start off with what our research goal is. It's not necessarily the most common research goal in robotics, which tends to be usually more specialized, but we're trying to figure out how to build a general purpose intelligent robot. That's not the same thing as general AI, but it's a robot that can do a variety of tasks in a variety of environments. So for example, if you think about, okay, so where I was saying that the goal is to try to deal with domain variability and also task variability. So the point is not to do one job super well. It's really to be able to, what would it take to make a robot that can do many jobs? So one way, one structure that helps think about this is to think about the distinction between what we call the factory and the wild. So the idea is, what we call the factory is we're building robots, and ultimately what we want to do is have a policy, some mapping from observations to actions that goes into the head of the robot in some sense, and we're going to send the robots out into the world. And the world is going to have some, there's going to be some variation in the world that determines the distribution of states that you face, the transition dynamics. There's some horizon over which the robot wants to work, and there's some reward. And reward is a general concept. It's just what goals you're trying to do and so on. So there's a, I'll be using this terminology of the factory, what happens when you're designing the robot and building it, and to get a policy, and the wild, which is where it's actually going to be. Now, in some sense, you could say that there's an optimal policy to be found, given that you have some distribution over rewards and worlds and so on. But it's very hard to find. This is not something that you can tractably do except in very simple cases. So let's think a little bit about the structure of the domains, of the domains. And I'd like to kind of characterize two axes of variation. One has to do with this idea that the environment is very varied. And as a result, the complexity of a near optimal policy, or actually any policy that has any chance of working, increases as you have a much more varied domain. So that's one axis. Another axis has to do with the uncertainty that in the factory that you have about the domain. So it's possible for you the classic engineering framework is that you have a very narrow task and you know what it is in advance. I want to build a robot that's going to weld, cars very well, and I know that. There's also a less common situation, but it's one towards which our research has been focused, in which you have what you want to get is something which has a broad competence. So a lot of the work that we do in planning has to do with how do you build robots that can deal with a wide variety of jobs. Now, as you go up the other axis, you could think that at the left end there's a narrow task which is not known in advance. And we'll talk a little bit later about that setting. And finally, there's the kind of holy grail, which is a broad competence in tasks that are not known in advance. So the question is, what should we be doing? And the claim is that we should be balancing overall effort, right? So there's how much a human has to do and how much the computer has to do. And really what we want is to construct, to pick a methodology for constructing robot systems where the overall effort is minimized. So since we're talking about constructing a policy, let's ask as a first step, how are we going to represent the policy? And the simplest way to talk about a policy is, well, you represent the policy as a policy. And maybe what we can do is search over the space of policies. And that's a well-defined methodology. The trouble is when you're trying to do something like find a policy to make dinner in an arbitrary house, these are huge policies, and any of the methods that try to search over the policies directly are sort of impractical for the kinds of settings we're interested in. So the other kind of very common approach is the idea of characterizing a Q function, a value function, an action value function over the states, and which tells you how good any particular state and action pair is. And then you simply max over the actions to try to get the action to do in a particular situation. And the idea here is that somehow dynamic programming is going to save you, so that you can only represent you represent the value with a state, not with a trajectory, and so you can reuse those values in multiple trajectories. The trouble with this is that, in fact, it's really only helpful if you're going to visit much of the state space a lot, because if you're going to only do one trajectory through your state space, you're spending a lot of time characterizing the values of lots of states that you'll never visit. So it really only works in situations like, for example, that are repetitive or reentrant, so you can reuse the state space a lot. Now, the techniques that I'm going to be talking about are mostly based on planning, and it's important to remember that a planner is a policy. That is, it's something that will map an observation into an action. You need to understand the transition dynamics and the reward and so on, but you can plan, execute the first step, and replan. So maybe that's not, you're in a situation where you need a policy to act very quickly. That might not be the right way to go, but in general, if you're interested in flexible policies, this is actually something that works reasonably well. However, if you're trying to do planning at the level of raw observations and actions, usually this is very difficult. You have to characterize the transitions in the space of raw observations and generate long sequences of torques, for example, in order to get an action to happen. So in practice, if you try to build a planner at the raw level, it doesn't necessarily work very well. So the kind of thing that we'll be talking about is planning more abstractly. So where in addition to having a planner, you have a perception system with that does in a classic estimation is one way of thinking about it, but basically finds objects, finds their poses and things like that. And there's a control system which has certain basic policies, usually parameterized policies built in. For example, a policy to go grasp an object or a policy to move from one location to another. I mean, just basic position control is one kind of policy that one can implement in a control system, and then define the planner in terms of that. Even this has issues because if you think about once again making dinner or something like that, the number of actions involved even at the abstract level is very large. So you probably don't want to do planning at that level even. So what we tend to do is we actually try to do hierarchical plan and execution. So what we have is we construct plans hierarchically, starting from a very rough level of the plan in which we've ignored a lot of the details that need to be achieved. And then we start refining it. And then at the end, once we get to a particular action that needs to be done, we do it and then do the replanning. So I'll tell you more about this later. Okay, so these are all different policy types in some sense. And the obvious question is, how do we get one? And I want to kind of work through a number of different approaches to kind of justify what we are doing as opposed to what some other approaches for this area are. So we've talked about classic engineering, in which there's a well-known task and I want to optimize and get some behavior. And I think today, and if you read a lot of the literature, you somehow seem to think that the only way to get interesting behavior is through learning, but it's not true. I mean, classic engineering can lead to amazing behavior. I mean, many of you have probably seen the Boston Dynamics robots, and this is Atlas doing parkour. That's a kind of unbelievable feat of classic engineering. I mean, this was done with classic control systems. There are other ways of trying to work in this same domain, in the same end of the spectrum. That is a well-defined task that you understand. That's very narrow and that you understand well, and you understand it, for example, by being able to build a good simulator of it. And you've all seen probably the OpenAI hand doing manipulation of a Rubik's Cube. This is also an amazing feat. But notice that, I mean, it is a very narrow task. It's not a broad competence. It can do this and not much more, just like that Atlas, can do parkour with that set of values. It can do parkour, but not much else. This is a kind of important point in the spectrum, and I'd like to spend a little bit of time because I think there's kind of widespread misunderstanding of the relationship between doing reinforcement learning in these kind of simulated environments and transferring them to the real world versus, for example, what it's involved in doing planning, the kind of more classic planning. So I'd like to kind of step through this a little more carefully. So in order to do most practical reinforcement learning, you need lots of samples, and you do that with a simulator. In the factory. That is, you don't do it in your home. You do it in the factory, and you do a simulation. And that simulation is what the RL algorithm is doing, is compiling a Q value or a policy, which you're then going to execute in the real world. Now, it's important to think about it, that in this situation, I mean, it doesn't matter how much reward you get during learning. It doesn't matter how often you interact with the simulator. All that matters really is what the effectiveness of the ultimate result and how much time you spent getting it. That's really all that's going to matter. Now, we'll talk in a second about how that compare, what's involved in the effort of doing an RL solution versus a planning solution. So what I'd like to now contrast is, something like RL, the classic RL in simulation setup that you would see, for example, for that OpenAI hand, and the planning approaches that I will be talking about, the one that we call hierarchical planning in the now. We've put a couple of entries on here, which you might find confusing. AlphaZero or AlphaGo is shown here as an engineering artifact that involves no learning. And that's because I'm going to reserve the word learning for learning something about the world. Whereas if you start off knowing the dynamics of the world, like all the rules of the game, there's sort of information theoretically, no learning. When we talk about learning, there are many different meanings. And so this is not learning about the world, but it is building a very complicated policy. So let's talk about this RL approach that we just talked about, and this compilation of the simulated experience into a policy, with what's going on when the kind of planning-based scheme that I talked about earlier. So this is the, the two pictures that I've shown you before. Let's think about what they both need. Okay, so one thing they both need is a characterization of the goal, right? So there's in a classic reinforcement learning formulation, you have a reward function, and in a planner, you have a goal. Now, just to illustrate this, this trade-off, I think it's worth thinking about. So I'm going to talk about, there's this suite of RL problems called Meta World, which is very interesting. There's like 50 of them. And they involve moving a Sawyer robot in XYZ and interacting with some objects on a table. The question is, what do the rewards for some of these tasks look like? I'm going to show you what's probably the worst case. This is a reward function for pick and place. I've pasted all the code into this slide here, but this is, the reward. Now, it's, you could think about this being a general purpose RL algorithm that's going to operate, but roughly what does this reward mean? So you can actually analyze it, and you see that reward has several phases, which involve several phases of the computation. It actually has state. In fact, you can look at it as a state machine, which has a phase of moving towards the object and then closing the fingers, then raising, and then moving towards the goal and opening the fingers and so on. And it's got, I don't know, 32 numbers that have been picked in it. So the amount of, this is, sort of a worst case, but it does show that if you're going to try to use a general purpose domain independent algorithm to do a wide variety of tasks, you have to have information about the task come from someplace, and here it's coming through the reward. Now, if you look at the planner that we've built to do these kinds of tasks, then this is the goal specification. And there's nothing about the structure of the solution from this just in the goal, but we'll see where we get our leverage. Okay, another thing that they both need is a URDF, a description of the robots on the task. Now, people, you could say, oh, a reinforcement learning algorithm doesn't need a URDF. No, it doesn't, but the simulator does. So at least in this setting, both sides need a description of the task that is in like what's the kinematic structure of the robot, if there are joints in the objects and so on, that needs to come in as well. The big difference between the two approaches is really in how you encode the dynamics of the world. So on the left, on the simulator, there's physics. So somebody, the Mujoko people, built into the simulator a theory of physics, computational theory of physics. And it's shared by all the tasks that use the Mujoko simulator. If you wanted to work in a different world that had different physics, you'd have to build another simulator. So it's important to treat that as an input. On our side, a lot of our leverage comes in the characterization and in some sense the physics of the world. And the way we do that is by building a set of operators, which are descriptions of the effects of the physics. It's a set of actions, which are the control actions that we can do, the pi a. So for example, moving in a straight line, grabbing something and so on, each has a set of operators that need to be characterized in terms of the preconditions for doing them and the effects. And then there are those controllers, which has the pi a, and also a set of features that are used for describing the environment. You don't want to think of states as just being state 1, state 2, state 3. You would think of it in terms of features. For example, what matters are the poses of the objects, or it's the masses and the poses, and so on. So that provides a kind of language for specifying goals, specifying the effects of actions, and so on. So really, a lot of the engineering effort in these two approaches is comparable. In many cases, people say, "Oh, I can run the RL thing without having to write any operators," but that's because you're building on the physics that somebody already did. So once the operators and controllers are written, then I don't have to write them anymore. So the next person who comes along, in principle, doesn't have to do it. So it's the same deal. Okay, so let's now think about the kind of planning, in some sense, the nature of the planning and the two types of approaches. In one case, for example, in the RL type framework, the action space is incremental joint torques or displacement, something quite low level. So that means that to do a task, you can think of there being like thousands of time steps. The heuristic, because you're doing search, right? You're trying to get to the goal or get reward, is a, some value function that you've computed on the basis of a lot of experience. And you need exploration because since you're trying to characterize what the value is everywhere, you need to kind of go everywhere and solve all the problems that could possibly arise so that you're ready, if they arise in practice, to act immediately. In the other approach, the action space is very different. When you write an operator, it's lifted in the sense that it's got in terms of variables. So it's not about specific objects, but it could be about object classes and so on. And it's compositional. Okay, so this is the big issue here, is that we can represent our knowledge in terms of operators that are compositional, so that I can combine them in different ways in different situations to achieve many different goals. So I can have 4 operators and do 50 tasks. So that's the key thing that we're going to get. There's a few other things that we get by being hierarchical. We tend to break the problem up into pieces that are manageable. And one important aspect of these kind of operator representations is that you can derive a heuristic automatically. There's a domain-independent approach to deriving heuristics from the structure of the operators themselves. And there's no need for exploration. You can deal with the problems and the states as they arise. I call this second part abstract model. So the question is, what are abstractions that are useful? And the abstraction on which our work is based is something which Hauser, Chris Hauser coined the term for, multi-modal motion planning. And the idea here is the abstraction is that the world is made up of kinematic chains, possibly rigid objects are kinematic chains, and the states are represented in terms of poses and a few other properties. Then you can think of modes, which are basically interactions. So for example, moving with an object in your hand, or sliding on a surface or whatever. These are modes. You can think of a mode as having a particular equation of motion or transition model that's specific to that mode. And when you get off the mode, the equations of motion change. Then there are, in general, mode families, which are the parameterized versions of these modes. Usually, there's an infinite mode family. So, for example, moving around in free space, depending on where the obstacles are, that's a different entry in the same mode family. So you can think of the problem of doing manipulation as one of moving, getting into a mode, moving in the mode, getting to an intersection with another mode, and then transferring to that mode, and so on. So this gives you an abstraction of the kinds of things that you need. You need, a controller to get in the mode, you need a controller to get out of the mode, and so on. So with that point of view, you can build a planner that, based on the description of the task in the URDF, actually does, can plan solutions for this. So, we built Leslie and I were working on a little planner, and when we saw the meta world thing, we said, oh, we can do these. We, coded up these different tasks. By coding up, I mean write the operators. There's a set of modes. There's free space motion, there's pick, move while holding something in place. There are some that involve operating like a door or a drawer or something, and there's some that involve pushing. So we were able to do 43 out of 50 of these reasonably quickly because we had already invested in having the physics, these operations already, we'd already done. So putting them together to do a new task is no problem. I mean, for example, in the RL version, moving to the left and moving to the right, the same object is a different task, partly because they're trying to do it from pixels, whereas we would, we use object detectors as a rule, so we can abstract away from that and we can do these tasks in a much more general way. We can put objects in the way and it'll move them out and stuff like that. So, this doesn't involve learning. It's very general, but it's very general. Okay, so what I'm talking about here is roughly an architecture for a system that has controllers, a finite set of parameterized controllers. It's got a perception engine that can do segmentation and simple shape matching, and it's got planning, which are characterizations of the preconditions and effects of the operators, and it's hierarchical. And this system is one that we've built in the past, and we call it hierarchical planning in the now. The name comes from the fact that this is the way it does planning. It constructs a plan at one level, then picks a goal to do, constructs a plan for that, then picks a goal to do, constructs a plan for that until it gets to a primitive and then executes it. And the other thing that it does is it does everything in belief space. That is, if you think about the output of the state estimator having uncertainty as a probability distribution over the states of the world, then what the policy that we build, that the planner implements, is a mapping from beliefs to actions rather than from states of the world to action. This allows us to integrate perception and planning. So we built such a system. This is one that Leslie and I built. It's code written by two older professors, so it's not beautiful, but it does. The same code can do a variety of different tasks, and it does integrates perception and action. In this case, you see it correcting, doing an operation of seeing it doesn't work and then correcting it. In this case, it was told to leave the room. It found two chairs in the way. It figured out what to do with the chairs to move them out of the way so it could leave. And all of this is done autonomously. It's been told to get a bottle that's full, and it's using the force sensor to figure out which one it is. And this is doing kind of a simulated and this is oiling an engine here. It doesn't look like an engine, but that's okay. And you can do it on a different robot. This is one time we went to Singapore and they had a fetch, and we ported the system to the fetch, over a few days. So it's a fairly general piece of code, but there's no learning here. It's just, Leslie and I did the learning, not the robot. Now, this is not a one-shot thing. Our student, Kaylin Garrett, has implemented this in a much nicer, beautiful way that's available on GitHub. That does also, is a general task and motion planning system, and he's implemented a belief-based version. This was done while he was on a internship at NVIDIA's lab in Seattle. But what you saw there was, it was asked to put the spam in the bottom drawer. It had to find the spam and then finally put it in the bottom drawer. So this is a belief-based planner. I'm not going to go into the details. There's a lot of details, but I will maybe pause right now. Are there any questions on this so far?
If you have any questions, you can type it out in the group chat, or you can use the raise hand button on Zoom. I've muted everyone by default just to be safe. So if you have any questions, do raise your hand or just type something in the chat box. There were a couple of questions, but they were, so there's a question: what if the spam is already in the bottom drawer?
Oh, it would open the top drawer, see that the spam wasn't there, open the second drawer, see it's there, and say, oh, I'm happy. So
Okay.
in fact, that's always the test that we run first on these systems is, if I'm at the goal, can you recognize it? So that would work fine. Anything else?
There's a follow-up to that. What if there is no spam?
Have you seen Star Trek? Smoke would come out. No, so one of the things that we always have to do is declare failure. That is something that, I mean, so one of the ways that, one of the things you can think about what the system is doing is trying to prove to itself that it can reach some state with a particular level of probability. So if at some point it has tried all the things that it knows how to do and it can't reach that state, it will say, I can't do it. But the problem is that it's going to take a while to fail because it's going to try all the things that it knows how to do. So recognizing quickly that it should fail is a difficult problem that we don't have an answer for.
Okay, awesome.
Okay, I'll keep going then. All right, so far I've told you about a framework for building planning. I probably came across as, oh, well, you know, you don't want to do any learning, but that's couldn't be farther from the truth. We do want to do learning, so let's talk about that. So far we've been talking about this bottom layer, which is basically operating in a situation in which we know everything in advance. So let's talk about what happens in a situation in which we don't know everything in advance. And so what's one alternative? Well, you could say, well, I could do RL in the wild, that is in your home. But if you try to do RL in your home, you would regret it. Because you destroy your home, and after a few years of experience, then maybe you would get your tea, but you might not be around. We don't have any practical methods for doing complicated RL in the wild. Now people are working on it, maybe someday. So what's an alternative? So what I'd like to talk about next is basically continual composable learning models for this hierarchical planning in the now. So the idea is the rough idea is to think of the planning system as a way of composing pieces. And the pieces are the operators, the models that we use in perception and so on, and trying to compose them in such a way that we can do a new task. So there's a bunch of things that we need, which are the ones kind of highlighted in yellow here. The blue boxes are fixed. They're algorithms, and they're domain independent algorithms, and we start off with them. Just like in an RL environment, you would start off with an RL algorithm that's domain independent and fixed. Now we have to put in these models. For example, I've talked about the operators and the models for the operators. You can also put in, for example, heuristic that is learned. We can get domain independent heuristics, but you might be able to improve them from learning. You can get some policies that you could use to do some common tasks. You could learn how to do perception in the particular environment that you're in. So all these are things that you could learn and to adapt to a new task. Let me start and mostly focus on operator models for new controllers and policies, and tell you a little more about that. So let's talk about skill learning. So if you are familiar with the robot literature, you will see that there are lots of papers on skill learning, and skill means something like cutting or pushing or stirring or pouring or throwing, and some closed loop policy that usually maps perception to action. So let's call that a skill. Now, what we want to be able to do is not just to learn a skill and be able to do that task at our thesis defense. What we want to do is acquire a whole bunch of them and combine them to do a wide variety of different tasks. So the learning doesn't stop once you've got the skill. You now need to figure out how you can combine them with other skills. So let's look at a particular example. So let's take the idea of pouring. So what I'll claim is that we don't want just a skill, we want what I've been calling an operator. And an operator is composed of a result, which is what the skill is supposed to achieve. And that result is in terms of features that I have in my domain. And that's a separate question of where those features come from, but let's take that from now. So there's a result that, you know, the liquid is going to be in the destination container, and there's got some skill, and that skill is a parameterized policy. It's a program that I feed in some parameters and it does something. And then there's a set of preconditions, which are values of variables or features under which the skill is guaranteed to, or at least with high likelihood, to provide a desirable outcome. That is, enough of the liquid is in the destination. Now, these, what I've got here, define the variables, the features that matter or could matter. You could imagine that a person gave you this, or somehow you got it from someplace else. Let's once again not worry about that. But one of the things that you would need is a characterization of the values of these parameters that would lead to a successful skill execution. So the question is, can we learn that constraint? So imagine that we have the other superstructure here of the which variables matter, but you know, we've actually worked on that too. But so what we're going to do is we're going to treat that problem of learning that constraint as a supervised training problem, and we're going to use Gaussian process regression to do that. So roughly what the way you think about this is you say, I want to learn a constraint, which we'll call the function g, which is a function of some parameters theta, and we want the constraint that g of theta is greater than 0. 0 is an arbitrary value. You can put in a constant in there to make it be whatever you want. Okay, so what we're going to do is we're going to take those parameters that were defined in the operator definition, and we're going to think about this regression, which is going to give us a score, g of theta. And we're going to take a bunch of labeled training example, and what does that mean? We're going to do executions of the policy of the skill in the factory and score them. I'll show you how we do that in a minute. And then treat that as a regression problem. We want a function that can predict the score. If you think of this as a Gaussian process regression, what we're interested in is that black line on the x-axis. That's an area where the mean value plus a standard deviation of the function, mean value is the red line, and the standard deviation of the function, which is the pink area, is above 0. Okay, so notice that within that black area in the on the x-axis, my knowledge of the dynamics of this, you know, this regression says that the function will, with high probability, be above above 0. This is sometimes called the super level set, high probability super level set. So that's what we're interested in. And what we're going to be doing is we're going to be choosing where to sample in order to sort of construct the biggest possible super level set. Now, one of the reasons, notice, you know, why do we want a super level set then rather than simply the best value? And the reason is the following. We're going to be using this in a variety of different environments. We're going to be pouring from the right, pouring from the left, pouring with obstacles in the way, pouring different objects. And so if you just find the best one, it's the best one for one particular setting, and it's not going to be useful in many settings. So what we need to understand is the range of possible values over the parameter values over which we can operate and still get a successful outcome. That's why we want the super level set. And that's why we want the characterization of uncertainty. So the kind of learning that we're doing here is using Gaussian process regression because it gives us uncertainty characterization. There are other methods that do, and they're fine as well, but that's this is what we're doing. So the idea is that, you know, we're going to get a bunch of training examples and we're going to use that to characterize the you know, build a super level set. And we've tried a variety of ways in the simple setting of simulated 2D pouring If you randomly choose your actions, you get roughly nothing. Leslie and I wrote an approach that used a neural network classifier and tried to optimize it. And it didn't work very well, but it did make our students mad enough that they did a better one. So here's the neural network regression, and finally the GP active learning. And you get, substantially better behavior by knowing, because of the estimation of the uncertainty and picking the values at the informative places. So as I mentioned earlier, we're going to want to basically sample from the super level set. So we're going to take an approach to planning in these hybrid domains in which we have parameters that are discrete, such as which object, and continuous, such as what angle to tilt the pouring for. The way we do this is we sample values and then we plan in a discrete domain determined by those sample values, sort of in the way that a motion planner such as RRT or PRM plans by sampling and then doing a graph search. So it's conceptually similar to that. So one of the things we want to be able to do is sample under diversity, and we use determinantal point processes as a way of getting diverse sampling, but I don't want to spend too much time. Okay, so it's important to realize whenever you're doing these kinds of things that getting robot data is expensive. Methods that tell you that they're going to learn using 10,000 samples and so on, in the real world, it's not practical. This is a highly sped up video, and our poor graduate students who are heroes forevermore are trying to get the robot to do the things. And this is actually a remarkably targeted data acquisition, because it's using grasp and motion planning during the data acquisition. So each of these actions has been planned to have some chance of success. If we were doing epsilon greedy actions in torques, nothing would work. It would take forever. So, we have used this approach to construct, simple scenarios in which, for example, this is a mix of operators that were pre-built by hand, the kind of pick and place operators, and then pouring and stirring types of operations that were learned. And the important thing is that we can combine them, right? So it's not like, I have a new skill and I have to start from scratch again and learn how to walk. It's a purely combinational scheme. So it has some chance of being able to scale to the complex systems. This is implemented using Kale and Garrett's PDL stream planner, which, as I mentioned, is available online. Okay, so there are other things. It's important to realize that there are other things that we can learn. I'm not going to have time to go through it, but another interesting thing that you can learn is search control. So one of the things about learn policies or Q value or whatever is that they execute very efficiently once you've learned them, and they get better with time or with more experience. Whereas the straightforward planner, you have to rerun it from scratch each time, so it doesn't get better. But it can get better if you figure out a way of taking planning experience from before and updating your heuristics so that if you're in a domain that has similar structure, then you should be able to exploit it. So we've actually worked on this, and we worked on a student of ours, Bumjun Kim and Luke Shimanuki. They've worked on a variety of different approaches to doing this. One that's interesting involves kind of selecting which high-level action, that is, it's an action which specifies the discrete variables, but not continuous variables, and learning which one to do first, or in a particular state, which one you should do. And we do it by learning a Q-value function in using graph networks based on a symbolic representation of the state, so it generalizes across many different states. I don't have time to go through with it. I can point you to the papers if you send me a an email. Ours works better than theirs, always. And so the point here is I've been trying to outline an approach to building a system that gets better with experience, that learns, but it does it in a compositional way. So you learn pieces and put them together rather than trying to build a huge end-to-end system that has to be retrained from scratch every time. So what I've outlined is, a little bit of the flavor of what that looks like. And I want to thank Leslie, who's a colleague who I've worked with for many years, and the students involved, Zi Wang, Kellen Garrett, worked on the combining operators story, and Ben Junkin and Luke Shimanuki, who worked on the learning the heuristic function. And I will leave you with outtakes from, you can tell that what we were doing is real because it doesn't work all the time. Okay, I'm done.
Awesome. Well, thanks a lot. I'm going to clap for everyone here.
Yeah, I'll clap. Bravo, bravo. Okay, we're done. Any questions?
Yeah, so folks, if you have questions, type it out in the group chat, or you can raise your hand virtually through Zoom, and I can unmute you. By default, I've muted everyone. So it looks like Dinesh has a question. I'm going to unmute Dinesh.
Hey, Pratap, can you hear me?
Yes.
Tom, thanks again for again, great talk, as always inspiring. So I like the point you mentioned about, you showed about working in everybody's home, and you had this comment that RL in the wild, and you gave some good reasons behind it. So, a lot of people, including myself, are using different learning methods, and I think we show promising results, but at least I don't understand the limits of learning methods. Do you have any sense of, we know the limits of previous kind of configuration spaces, methods, and all that stuff. Based on your experience, do you have any sense of what the limits could be, what we could do well, what we could not do well?
Boy, that's the $64 million question, right? I don't think we know. Now, I mean, we do, there are two different kinds of limits you could talk about. You could talk about what the limits of what is learnable, and the limits of what it's practical to learn given the experience that you're likely to get. And the real limitation, at least in the near future, is really that. So many of the breakthroughs, and they are breakthroughs in deep learning, have come because of the availability of enormous amounts of data. There's a problem with data in the for robot problems is, it's not, you're not trying to learn a function from one fixed input to another. It's you're trying to act in the world and affect the world as you go. So the amount of data that you need is astronomical, and that's the real limit. In fact, I mean, I think that as far as learning in the wild, we're severely limited. I don't think we can do much right now. Now, roughly everybody's betting on the idea that we can build simulators that are good enough that you can learn most of it in the factory. And then when you go into the wild, you will be able to, you'll be ready, and you'll need only a little bit of data. I think that assumes that the learning system can generalize more than I think that they can, or that we know how to do right now. So I think you can do great things, but I think there are, a lot of practical limits. That's why what we're trying to do is to try to break things down into little pieces that can be combined, because then the complexity of and the amount of data that you need to learn each of those little pieces is much less. So that's the whole idea.
Dana now has a question. I'm going to read it out. I assume your domain independent heuristic functions are pretty different from the ones that AI planning researchers use, things like relaxed planning graphs, etc. Could you say something about what they are like?
No, they're exactly those. For example, what PDDL stream, which is Kalen's version of the task and motion planner does the simplest version is you have a domain that's hybrid that has discrete variables such as a PDDL AI planning domain does, and it has continuous variables such as the configuration of the robot and position of the objects. So what you do is you sample a set of values for those continuous parameters. That creates a discrete parameter, which is encoded in a PDDL file and handed to fast downward, which is a standard AI planner to solve. So it's using exactly those heuristics. The one that Leslie and I do is a little different, but not much. I mean, what we do is, instead of using an and/or graph for planning, you simplify it, you relax it, so that you only do the ands or the ors. So this was the domain-independent heuristics were inspired directly. Inspired, that's another word for copied from the AI planning community. I mean, the big problem with the AI planning community is they're allergic to numbers that are not time values. So, we have to deal with lots of numbers, configurations, but geometry and so on. So we have to do this additional work to be able to use their code, but we use their code.
Awesome. Yeah, so Dana says science, and he would like to see some pointers to papers about that. And I guess you can follow up.
Look on our website. There's at least 50 or 60 of them.
So John Barris has a question. I'm going to unmute him.
Right, so we talked about before, very nice talk, but I have the following question. Suppose you go to the task where you try to pour something into a glass, right?
Yes.
I don't know how many times you tried that yourself, but depending on the amount of liquid and the relative positions, sometimes you have to adjust to make sure that you're hitting the target.
Yes.
I was just doing this morning, and I was, throw things off all over the kitchen and all that stuff, and I got to go back and forth. Okay. So where is that captured? This adjustment online to the variability from the pre-planned thing to the actual thing in your framework.
Right. So the way we're doing that now is the controller is a parameterized controller. So if it's going to do online adaptation, it has perfectly fine with access to the perception. There are some parameters. For example, you might imagine that there's a gain associated with that. Okay. And what we're going to do is select the gain or learn the range of gains under which it works. But it's a policy, it's a feedback loop, and it does what it does. And at the moment, we've separated that. So you could imagine having a feedback loop that doesn't adapt online. You could have one that adapts online. We're agnostic as to that. The thing that we care about is doing the learning to characterize the conditions under which it works.
I see.
And then we pick those parameters.
And another thing I run into when I try to do composable design is where do I stop? Meaning, if you create too many components, then putting them back together defeats the purpose. So you have to actually find the right amount of components so that, as we do, for instance, component-based software or component-based system engineering, so on and so forth, so that you have the right balance between the number of components and the cost of putting them together. How is that handling your framework?
Yeah, in the AI community, they call that the utility problem. So when you're learning operators or you're learning macro actions, if you add too many of them, then the matching factor increases, and then you're dead. We mostly deal with that via hierarchy.
I see.
We don't really have a general answer to this. It is an interesting problem, but the way we try, well, there are two things that work towards trying to give us efficiency at some level. One is heuristics, and the other is hierarchy. And there are several different kinds of heuristic. There's the classic heuristic, which is evaluation of at a node, at a state of the distance. But there's also ordering which you consider actions at a node is another thing. So if you could have lots of operators, but you you learn a function that tries to select them in order of likelihood of success. And then by using hierarchy, we abstract away some of the the conditions of the operators, and some of them get merged that way. So we don't have a general answer to the problem. It's one we recognize, but we do have some techniques to ameliorate the problem.
Thank you very much.
You're welcome.
So we have a couple of questions on the chat. For the videos where you annotated there was a speed up of 8x, what do you consider to be the bottleneck? What would it take for the robot to act more naturally or quickly?
I'm asking for volunteers to code in C++ instead of Python. Anybody raise their hand? You can raise it on the chat there and send me your email. This is all experimental code. It's all written in Python. We don't try to, I used to, okay, I'm an old guy, so old guys tell stories. Let me tell you a story. So I started doing motion planning in the 1970s. And when I used to try to talk about that, people used to say, oh, but that's going to be hopelessly slow, right? So, you know, I heard that for so many years. I finally left and did computational biology for 15 years because I couldn't take it anymore. Then I came back after 15 years and motion planning is fast enough, everybody uses it. Okay. So then I started working with Leslie on release-based planning and so on. And then I went to give my first talk on this stuff. It was on a workshop at ICRA in San Diego. And I gave my talk, beautiful talk, of course. Are there any questions? And the guy says, isn't this going to be hopelessly slow? And I went, oh my God, you know, it's as if I was never away. So my answer at that time was, wait 15 years. So I'm tempted to give you that answer again.
So one last question. Do you think building a policy through discrete skills would be robust enough to handle uncertainties in real world environments, things like perception glitches, external disturbances? How do you address robustness of individual components? And then sort of when you put it in the system, how do you handle robustness?
It's important to remember that these skills are all hybrid. There's a discrete number, but they're parameterized. So, and each one of them is a feedback loop. So that's the first level of answer. The second level of answer is that it's all in belief space. And the way it works is you do something, you get an observation back, you adjust your belief space, your belief state, and then you go again. So the whole point is to try to get robustness. It is not, I mean, you cannot do this by having a set of fixed actions and somehow doing them and hope that it's going to work. You still have to sweat the details of getting, you know, the object detector gives probabilities of, you know, of the correct, you know, here's a pose and here's a probability distribution. So it's all operating on Gaussian distributions and so on. And there's discrete type uncertainty in the system and all of this. So we haven't solved the robustness problem, but a lot of the architecture of the system is motivated by this problem of robustness, which, I mean, dealing with uncertainty is the reason for our being. That's what motivates the whole thing.
Awesome. All right, so any other questions from the audience, from the students, MRC students? If you have questions, type it out, raise your hand. Yeah, David has a question. I'm going to unmute him.
Kind of following up on the previous question, I guess, could you just speak a little bit more? Like I looked at the PDDL stream paper briefly, and it looks like in the simulated experience, there's some teamwork and interaction with other agents. Can you talk more about how these methods handle a changing world and other agents like that?
The work that we're doing in the robot doesn't assume other agents or exogenous events. It's a single agent. It's a classic planning problem. Yeah, so we haven't done that. Now, Kalen, in his Pillow Stream work, has, in order to show generality, has extended it in various ways to deal with some simple multi-agent problems. He's also, instead of using fast downward, he's used one that does time, and so he can set up some problems that involve time. So because it's using black box planning, any planner you can put in there, the language is, it's an extension of PDDL, and you can deal with a variety of different problems. In the robot domain, certainly all the examples I showed you, it's like a classical planning domain. It's a single agent and scripts assumption.
A follow-up question: in the experience you showed, how much variability was there in like the setup? Like I noticed that there was some random fuzzing done in the simulated experience, but did you like put the cups in different places or something somewhat?
Yes, okay, so perhaps it's not clear, but it's using object recognition to locate the objects.
Yeah.
So that's in the loop. So you can start off with any arrangement and it'll do the best it can.
Okay.
So it is not a pre-arranged thing. And
well, sure, yeah.
Yeah, no, it's this particular system that was running here. It has a CNN network which recognizes a set of objects that are on there that we trained, and it looks at the scene, finds the plane, places the objects on it, then does planning from scratch to achieve the goal, and it's completely general with respect to the position of the objects.
So one cool thing about doing this over Zoom is, looks like Kalen is online, and he's been sending links to the paper in the chat window in real time as you've been describing.
Oh my God, what, did I say something bad? Kalen, are you upset? No, yeah, no, Kalen is the man. You can ask him. I can get off. Yeah, yeah. So Kalen has code online, and you're all welcome to use it. It's awesome.
Awesome. All right. So unless there are no more questions, I would like to thank Tomas. I'm going to clap on behalf of everyone. Thanks for giving us the virtual talk.